Good evening, everyone. Welcome to the week 3 PL Sour. How is everyone doing in the past week?
It's going good. Thanks, Jerry.
Sounds great, Stephen.
How are you doing? Are you surviving? You surviving week 3, Jerry, in your program?
Yeah, almost. Yeah, I've been trying to make some feature projects on my LinkedIn profile. Basically, a data analysis report, because I'm also looking for data analysis jobs. Yeah, but to make a sample project, it also takes lots of time. I was studying about cross-validation, and it takes so much time that my program is still running after like 1 hour or 2.
Sounds intense. It sounds more intense than linear regression.
Somewhat, but they are all connected. So for example, the problem I'm working on is that is to select predictors, or maybe you would name them as explanatory variables, because I have quite a few. So a typical way to select the best predictors among all available predictors is to use cross-validation. So the content we're going to learn in this class about linear regression is actually the basic or the base of many additional and advanced methods. So I hope you can handle them pretty well. So in the future, if you add on additional techniques, you will learn much faster. So has anyone started working on homework 3? And let me know if you have any questions regarding homework 3.
I got a question. So when doing I don't have the homework in front of me, so I'm sorry I don't have the question to reference, but there was a question about using the regression equation to estimate the price of a bicycle. And I was looking at the historicals. We were given like the 10 observations. So I used the equation and typed in an actual from the observation, and I got an answer that wasn't, it didn't exactly match with one of the actuals, if that makes sense. So if, let's say if the weight was 15 and a half pounds, yeah, I got a price that was different than what was given to us. Is that just because the model is not 100% perfect, but it's, it's a prediction?
Yes, correct. I think in the videos and handouts, you learned the distinction between observed values and predicted values, or maybe you call them fitted values. And this distance or difference is called error.
Got it. Okay.
Yeah.
Okay,
so the predicted value usually has some deviation from the original or the observed or the actual value. However, the algorithm of a linear regression is to minimize the sum of squares of these errors.
Okay.
Yes. So it's quite fine if you see that the predict value of your model is somewhat different from the actual value observed.
That makes sense. And if the higher the R square, is it the more accurate the prediction?
Yes, correct.
Okay. And for some of the questions, it'll ask like, what is the R square, for example.
Mhm.
So you'll put a number there, and then it'll say, what does this tell you? Or to elaborate on that,
Mhm.
how much detail are you looking for in those types of open-ended questions?
Okay. Well, can you possibly give us your example you're working on so that I can start from
Yeah.
there?
Yeah. Sorry. Let me get back to the computer, and I can just pop it up. And
Yeah, I think you're probably referring to part B of problem 1. So in problem 1, we have some bicycle data about its price and weight. And in part B, the question is about the correlation coefficient between the weight and
yes.
price, and what we can expect the coefficient of determination is for this simple linear regression model. Did you want to ask a question from this part?
That one in part D. So B, I mean, I just put
right.
yeah. So for B, I just put what I thought the value is for coefficient of determination, and same for correlation coefficient. That was the response.
Wonderful. So you want to ask about how to address questions like part D?
Yeah, I mean, I put like I have a one sentence response that just would that be sufficient, you think, or is the professor looking, or are you looking for
Yeah, you don't
kind of
have
more
to
of an
make it
elaboration?
long. How about
Okay.
you present with us the one-liner you had about this goodness of fit measure?
I wrote, so for part D, my response was only 90.5% of the variation in bicycle prices is explained by the weight.
Oh, I see. However, this is not a correct answer.
Okay.
But can you repeat the answer, your answer again?
Yeah. Only 90.5% of the variation in prices is explained by weights.
The structure is pretty fine. However, this 95% is not correct. What you put here is the correlation coefficient, which is about 0.95. However, here, the percentage of variation explained in the y or the dependent variable from the independent variable is not this correlation coefficient, but the squared version of it. So instead of a correlation coefficient here, you must look for either the R square or adjusted R square in the summary output of a regression table.
Sorry, I think I maybe misspoke. 90.5%, not 95%.
Oh, you
So
said 90.5. Okay.
yeah, sorry,
Yeah,
I probably
that
came
sounds
across
good.
jumbly. Yeah, okay. But okay, thank you.
Yeah, sorry, I guess I misheard what you said. How about other students? Did you have any questions regarding the distinction between a correlation coefficient and this measure that we use to describe how well a model fits the data? What I meant is that the statistic you report for part B should be different from that one in part C. Oh, sorry, part D.
I was having a little bit of trouble determining the error or the residual value in part C of problem 1. I was using the, let's see, the regression model to determine that, but I'm not sure if I'm using it correctly of the residual. It looks like gut check. It might be correct, but I'm not sure if I'm reading it correctly, the regression model, to determine that it is correct.
Okay, I'm not sure whether I completely understood your question, since you said you already fit a linear regression. However, you're not sure where to put the residues. Is that what you wondered?
Yeah, so
the question itself asks us to develop a model, a linear regression model particularly, and we simply report the regression equation. So where did you find the residues problematic?
yeah, so, well, from my understanding, the equation for regression is the intercept plus the slope multiplied by the independent value plus the error, slash residual. Is it just asking for explanation of what is a regression equation, or what is the regression equation from the problem? Because I guess
Okay. Let me see this. Okay, so I guess you actually wondered how to report a linear regression equation, right?
Yeah, I'm happy to share my screen if that might make it easier.
Yeah, sure. I was also about to share mine, but it sounds like you have already prepared. So let me enable your sharing. So now you can share your screen with us, and let's see whether you made the linear regression model correct, and let's find out a way to report a regression equation.
So I'm using
Excellent.
this intercept as the intercept. This as the slope. The independent variable, I just have it as whatever I can link into. So
I see. So you were trying to set up a line of functions to report this model. Okay. And I guess you were wondering what value to put in this error, right?
Yeah, so I thought the residual would be 8, but I'm not entirely sure if that's correct.
Okay. All right. So first, this is not the typical way to report a regression equation, but I really like your innovation here. It's my first time to see that linear regression is worked out by plugging in this equation you're setting up here. However, looking at your values, it looks totally fine, except that this error, right? Yeah. So the value you're currently quoting here as 8 is not an error value actually, but here is 8 means the degree of freedom for residues. That actually means because we have 10 observations, that means 10 rows in the original data, right? And we have 2 parameters to estimate. But the first one is intercept. The second one is the coefficient of weight. So if we take out these 2 from the original 10 value, 10 observations, that's what this DF means. The degree of freedom is 8 because it is the value of the number of observations minus the number of parameters to estimate.
Okay, so just to clarify, if this was still 10 observations, but there were 3 parameters, this would be 7 then?
Yes, you can test it yourself. For example, if you can create another arbitrary column, saying maybe parent, or whether the bike is mountain or road bike, you can create it for yourself later. And
Yes.
you will find that this residual degree of freedom is exactly, as I said, the number of observations minus the number of parameters to estimate. Yeah. However, to address this question, let's see what we should, how we should report linear regression equations. So let me share my screen, which has essentially the same content as what Paul already showed us. However, let's practice on writing a regression equation out of the summary report. As you can see here, I built a summary, I built a linear regression model using weight to predict price. And I had the same exact result as what Paul and Stephen had. So a linear regression equation would be something like this. We write as the dependent variable, which is price here, equals the intercept. So usually for any number larger than 100, I'm using the APA, the American Psychological Association style of presenting statistics. For numbers larger than 100, we simply take the integer part. So this is the intercept, and we need to consider the weight. As we know, weight, the price would be higher for lower weight bicycles. So here we would include this number as 1,500. And we continue writing it times weight. So this is simply the linear regression equation that we should have. Sometimes you would also write error part, and this simply represent error. So this is what you call a regression equation. So we don't need to put a specific value for error. And we simply write the equation as an equation. We don't have to fit in specific values of observations for weight. However, we can use this equation to predict specific values. And to predict, we simply take error equal to 1. Error equal to 0. So we don't predict errors at all. So for example, if we want to predict the price of a weight equal to, for example, let's see, 16.5, which is not included particularly in among these 10 observations. So we could write it like this. So for weight equals to 16.5, the equation would be like this. Yeah, so we simply leave the error like it is here. But if we do want to have a specific value, that's when we need to simply assign 0 to this error. And it'll be like this. So here we would call this is the expected value of the price for weight equal to 16.5. And we can actually calculate this value using the way that Paul worked with. So we can use a function that's equal to the intercept remember that we need to use plus here, although because the coefficient is already negative here. So we plug in 16.5 as what we wanted, and this would be the expected value of price of a bicycle with a weight of 16.5 pounds, right? Yeah. I believe the unit is pounds. So did this address your question, Paul? So for part C, we simply write what we have in this cell, and that's what's known as the regression equation. We don't need to plug in specific values for either the error or the weight.
Just had another question. Just want to make sure understanding correlation coefficient correctly, because the correlation coefficient is the same as multiple R, but multiple R will always be in absolute terms when it does the regression statistic, I'm assuming, because from what I'm seeing, the relationship is negative. But multiple R is producing a positive.
Okay, so your voice passed to me is had some noise, so I couldn't hear clearly. But you were curious about the distinction between multiple R and the correlation coefficient, am I right?
Yes, correct.
The similarity is that the multiple R is actually one kind of correlation coefficient. However, this one kind is actually between the fitted value and the observed value of the dependent variable. Here, it'll be the price. So this multiple R is the correlation coefficient between the predicted value of price and the actual value of price. And a correlation coefficient can be between any two variables. So you will find the distinction more apparent when you have multiple regressions, which I believe we don't have at this moment, and we will have practices with predictors of more than one in the future homework. So for example, you can actually find out these are equivalent in this case. So for example, this is the correlation between weight and price, right? And you find this value to be negative. Yeah. However, you find here it's positive. The reason is that if we create another column saying expected price, or you can say it as a predicted price. And by this, of course, we can use the model result to predict price using weight. So we use our model result here. We use intercept plus the coefficient times weight. And remember, since we already learned the relative versus absolute reference, here we want to use the absolute reference for the coefficient because the position of these cells do not change. Okay, so these are the expected values, right? So if we calculate this correlation again between the expected values, and the actual values. And you will find that this number is exactly the multiple R. So that's what I meant. Multiple R is the correlation coefficient between the dependent variable and the expected value of the dependent variable. However, a correlation coefficient can be built between any pair of variables. And usually we would assess this correlation between a predictor, which is an independent variable, and a dependent variable.
Would you mind just highlighting the cell D13? Okay, I see. So your
D13.
correlations. Okay.
Yeah, so
I see.
here I use the same way we derive correlation coefficient.
I
However,
see.
notice the distinction between cell B13,
Mhm,
which is assessed from these two columns, B and
mhm.
C, which is weight and price, or X and Y in our model. But here, the correlation coefficient is built from the price and expected price, which is Y, and Y hat, or expected Y.
Mhm.
Y hat is usually a symbol of the predicted value of the dependent variable.
Got it. Got it. Thank you.
Yeah, I'm glad that you have noticed these small details, which is pretty excellent. So any questions regarding homework 3? I think the questions and examples are pretty straightforward as long as you went through all the course materials. You should have a good understanding of what to report. Oh, right. I forgot to mention that. Did you notice the relationship between these three values? If you simply use another function of so you can do this. If you take multiple R and take a square, then you find that this is exactly what it'll be. This multiple R to the power of 2, then these two values are exactly the same. So this is how R square is calculated. It is the square of the correlation coefficient between the dependent variable and the expected value of dependent variable. Can I have a volunteer to tell me whether we have learned already what the adjusted R square here means? Have we already learned that in a class?
Not that I remember. Not sure if anyone else
All right.
maybe saw it. A video
It's
on it.
not. It's quite fine to leave it for now, because we will learn it in the future when we have more than one independent variables as predictors in the regression. Because the adjusted R square is only useful when we have 2 or more predictors in the model. And the use of it is to adjust for the bias in R square, because in the future you will learn that R square is usually it goes higher and higher when we add more and more predictors in the model, no matter whether it's actually useful or not. So in those cases, when we have more than one predictors in the model, we want to actually focus on the predictors that are important for the model. That's that's where we need to use the adjusted R-square to assess the model fit instead of R-square. And simply you can notice that the adjusted R-square value is somewhat lower than the R-square. This is always true. So this is kind of a preview of what adjusted R-square indicates for models with more than one predictors. Has any of you started working on problem 2?
I took a shot at it, Jerry.
Oh, excellent. So have you run into any questions from problem 2?
For the beta, I ran the regression,
Mhm.
and I just took the slope for the beta from that model. I did not candidly use the YouTube video and whatever equation came from that. Is that okay for this assignment, or?
Oh, okay, sorry, I missed your question. You already fit the model,
Yes.
and you want to address the question about how to interpret the slope, and
So
you missed
I took
some videos.
no. So there's a video on how to get the beta,
Yes.
how to calculate the slope. I did not watch the video, and instead I just ran the regression and took the beta or slope from the regression. Is that accurate? Is that a correct way to do it?
Yes. Okay. I guess your confusion actually comes from multiple terms referring to the same statistic. So
Okay.
that was Stephen, right?
Yes.
Yeah. The slope can be referred in a few ways. So in the Excel regression summary output table, that's what we showed earlier.
Mhm.
It's known as coefficient. It's also slope because that's what we first learned in other parts of the statistic, and slope is more, they refer to the same statistic. And sometimes these are also referred to as parameters because that's what we need to estimate. You can also find, are there any other ways to refer to them? I think basically they're mostly known as coefficient. And in the questions, when it says slope, it actually also means coefficient.
Okay, so that's what I did. I just took the coefficient from the regression outputs.
Nice.
Thank you, Gary.
All right. Oh, okay.
Just from my understanding for part B is that means that the model was not a good indicator of the movement, given that the R-square is much lower compared to the well, I guess in comparison to looking at the bicycle problem.
Sorry, your signal was not that good. Could you repeat your question again?
Yeah, no problem. Apologies. Not sure why it's like that on my end. But my understanding is that the R-squared is lower, much lower at 0.36 compared to the bicycle problem.
Oh, okay.
So,
yeah.
Yeah. So that
And
shows that it's not a good model representative of. the stock movement to the market movement.
Yes, you could interpret that way. However, the comparison between R square of different models, that means one model predicts predict variable A and the other predict variable B, is usually not compared directly using an R square. However, the meaning of the R square holds. That's the percentage of the variation in the dependent variable explained. So as we found out earlier, in a bicycle model, the R square is about 0.905. And in the Microsoft stock price example, the R square was, as Paul said, 0.36. So the difference between these R squares suggests that the first model grasps most of the variations, but the second model does not. So in the second model, for the stock price model, much of the variation in the dependent variable is not explained by the independent variable. And in addition to that, I want to point out that don't panic if you ever fit a model where you find the R square to be somewhat lower than what you want it to be. So generally for a multiple linear regression model, depending on the sample size, an R square about 0.1 or above are all accepted. And it really depends on the purpose of your analysis. If your purpose is to predict the dependent variable as accurate as possible, then we of course want an R square as large as possible. However, lots of times the purpose of our study is not to predict the dependent values. Instead, we want to assess the relationship between the dependent variable and the independent variable. In this case, it doesn't really matter what the R square is, as long as we find out the actual relationship, then it's good. All right, since we went through the slope question, as Stephen pointed out, how about we make some practice on how we interpret the slope? I would like you to suggest some of your answers in the comment about your answers to problem 1 and question problem 1 part, let's see. Part E. So you can copy and paste your answer to problem 1, part E in the comment. And we can exchange some answers to this question, how we can interpret a coefficient or slope.
Sorry, I just joined. Can you repeat the question one more time, please?
Oh, hello, Ziyu, welcome. We went through some questions on homework 3, and currently I was hoping to make a practice of interpreting slopes of regression summary tables. And we are working on problem 1, part E. What change in price would you predict for every additional pound in the weight of a bicycle?
Oh,
So,
C or I'm sorry, number E, right?
yes, correct.
Oh yeah, I got the same as Stevens.
Okay, so do you mind elaborating your answer?
So what I did, I'm using that equation. So which is and also the change is the slope.
Okay.
Because it's additional, every additional pound in the weight. So the change is the slope. So it's negative 1,528.6.
So would you mind quoting the complete sentence where you interpret?
Oh, that's my answer. Oh.
Oh, well, if you have worked it out already.
Oh, yeah.
Or you can simply put in the chat area. So what I seek is not a simple value, but a full sentence where you interpret a slope. So Paul had supplied his answer, saying that for every additional pound, it would be negative $1,500 for every pound lost. Okay. And Ziyu said, changing price equal to negative 1,500 for every additional pound in the weight of bicycle. Yeah, I can see that you understood, both of you understood the concept correctly. However, this may not be the best interpretation when writing it. So it's better if you phrase your interpretation in a more easier to understand way.
Jerry, would it be something like for every additional pound in weight, the price would decrease by $1,528.56? So,
wonderful. Yes. What Stephen just said is a great example of interpreting a slope.
Thank you, Stephen.
Yeah, the difference between the examples Paul and Ziyu listed in a comment from what Stephen just said is that in a professional report, you usually want the version what Stephen had instead of what Paul and Ziyu listed here, since we want a more formal language, and which is concise and correct and also specific. Yeah, so the 3 point I quoted just now are all important in writing reports. The first correct is that you need to have a correct understanding of what a slope means. For concise is that you don't need to repeat the same message again. For example, in Paul's example in a comment, the number of 1,500 was used twice, so which is not necessary. And the use of loss and negative is also contains some repeated information. And for specific is that when writing reports, we do need to be specific in terms of the quantity. For example, quoting the slope, the value of $1,528 is important. If you did not use this number, it does not provide a clear message to the readers of how large this effect is.
I see. Thank you.
No problem.
Hey Jerry, I'm having a hard time running the regression routine for the data for number one.
I see. So
How do you use the toolkit? You just use the data analysis?
um, yes, you need to enable it in the file tab and options, I believe. So how about
I'll share
I
my
have
screen.
a volunteer to run the regression again, so that we can share the screen and see how you derive the regression summary output.
Okay, do you want me to share my screen?
Yeah, you can do that. Have you already generated the summary output table?
No, I don't know how to do it.
Have you already started sharing?
Yeah, I started sharing.
Oh, wait. Oh, okay. Wonderful.
So do I go to here?
Yeah. And did you find the regression?
Oh, I see.
Yeah, these are illustrated specifically in the videos. So make sure you read the meanings in each of the tab.
Okay, and then just say okay. Or need the residuals.
Yeah, you can click each of them and find out what the options actually mean. But we can start from here. You can click OK and have, oh, all right, yeah. You select as to save the output
Oh.
in a new worksheet, which is fine.
Sorry, I messed this up.
Yeah, so while Mark is working here, I want to point out that in these two cells for input Y and input X, make sure that you include the first row, which is the variable name. If you don't, then they treat Excel will treat the first row in the specific range as the name of the column. So you can lose one of the 10 observations if you don't have the variable name selected in the range.
Oh,
Yeah, as you find out here, you have exact same results as what we practiced earlier.
got it. Thank you.
Yeah, so here is the residue output you selected to generate.
I don't need it.
Yeah, at this moment you don't. However, you can also find what it includes. So it tells you the predicted price and residues for each of the observations.
Oh, okay.
Yeah, so those can be convenient when you want to assess the relative the relative size of various residues. So for example, if we go to sheet 1, where you had the additional section of residues output table at the bottom, we find, for example, for the first observation, when the predicted price is about 3,000, the residue is in the size of 400, which is okay. We basically, here it means that we overestimate the price by 400, because the original price, if you go back, you will find that it's about 2,500. When we sum the predicted value and the error, that's when we get the original value or the observed value. So by assessing the residues, you can also find whether it's how much the residues are compared to the predicted or the original values. All right, any more questions about the homework 3?
Yeah, give me 1 second. Let me see. Now I'm just a little bit worried about my wording. Like,
okay, what questions are you working on?
So first, the problem 2, it says, it asks us what is the slope, and I actually wrote it. It is, but what does the slope say about Microsoft? So I can put in a chart, a chat, right?
Yeah, you can do that, and I'll take a look. Yeah, earlier, I think it was Stephen or Paul had a question regarding what it means by slope or beta or coefficient. And just to be clear, they all refer to the same thing. So no need to be confused by the different ways of referring to the same statistic.
So I put in the chat, I'm just saying, like, the slope beta is 0.9057. So it's like when S&P 500 goes up 1%, Microsoft stock price goes up 0. It's not 0. It's the, it's 0.9057%. So when it goes down 1%, it will go down 0.9057%, which indicates that Microsoft stock is less riskier than S&P 500. I don't know if I need to add this on, or is it accurate?
What you wrote there is excellent.
Oh, okay. Thank you. And there's a B.
In the chat area, you will find that Ziyu's answer is both correct and also very informative. What she said is when she said it indicates that the Microsoft stock is less risky than the S&P 500 is actually what it means, because the coefficient is less than 1.
Thank you. And that's it. And the second question, I write it very simple, but I'm not really sure. So what is the R square of your regression model and what does it mean? So I calculated 0.3 3608, which just means like 36.80 0.08% of the observed data fits this regression model, which doesn't fit well, which it means like it didn't fit that well.
No, it doesn't sound correct.
Yeah, that's what I mean.
Could
like,
you, maybe copy and paste your answer in the chat so I can see it clearly?
I copy pasted.
Let's see. So Ziyu was working on problem 2, part B, about R square, and she wrote R square equals to this much. It means 36% of the observed data fit this regression model, which doesn't fit well. Unfortunately, this is a wrong understanding of R square, but particularly it's not the observed data fit that's reported by the R square. It's the percent of variation in the dependent variable explained by the predictors or the independent variables. That's what an R square means.
Oh, so what you mean, like the explanation was on the right track, but the one that it says observed data was wrong, right? I understand now because it was the change of percentage. It's not the data actually.
So there's no change involved here either.
Oh, sorry, I missed it. Okay, can you repeat one more time?
Yeah. So an R square is the percent of variation in the dependent variable explained by the dependent. Oh, sorry, wait. Let's start again. An R square transformed into a percentage is the percent of the variation in the dependent variable, which is Y, or monthly changes of Microsoft adjusted stock price here, explained by the independent variable, which is X, or the S&P 500 stock price change. Yeah. So, or in a simple version, how much percent of Y can be explained by X? That's what R square means. And this percentage is in a variation. And you can perceive it as, there are quite many different observations of the dependent variable. Here, I think we have about 130 observations for the stock price case. And the stock price of Microsoft varies, or actually the change in the stock price of Microsoft varies between these 130 months, right? So how much of these variation can be explained by the change in S&P 500? Let me find is 36%, which also means that there are another 64% of the variation in the Microsoft stock price change that cannot be explained by the S&P 500 stock price change.
Oh, it means like it was not correlated, like these percent, the X and Y?
Oh,
Dependent.
well, I'm not sure whether you were here earlier when we explained the distinction between correlation coefficient, multiple R, and R squared.
Okay. No problem. I will.
Did
I
you
can
listen
look
to
at
that part?
No, I didn't, but I don't want to waste other people's time, so I can watch the recording.
So you will find that the R squared is simply the square of the multiple R. And multiple R is the correlation coefficient between predicted Y values and the observed Y values. Yeah, and as you can perceive, if our model predicts the dependent variable really well, so that the predicted value is almost equal to the original observed dependent variable, then we would expect that there's a correlation coefficient of 1.
Got it. Thank you.
All right, thank you for joining us with addressing questions about homework 3. And I hope to see you again next week.
Thank you, Jerry.
Thank you, Jerry. Bye-bye.
Have a great weekend.
Thank you, Jerry.
Thank you, Jerry.
Bye-bye.
Jerry.